Hubble Fellow and former Einstein Fellow. She's been doing postdoctoral work there. She received a bachelor's in physics from MIT in 2006, finished her PhD at the University of Hawaii in 2010, studying long gamma-ray burst galaxies using the Keck telescope, which all of us would like to do. She is engaged in long-term research now on the astrophysics of massive stars. That's her field of study. I think that the sun is pretty weird. When I started learning how the sun really works, what little I actually know about it. I actually never got past the the CNO cycle, but when you get to stellar systems, especially closely orbiting systems, it gets weirder still. Massive stars are absolutely mind-boggling. So Emily is going to tell us something about massive stars and some other things tonight, and Dr. Emily Levesque.
Yeah, I was going to ask you to take down the overhead. Perfect. And then can everyone in the top see the whole screen? Okay, I just wanted to make sure everyone can see the whole thing. So, as has already been explained, I'll be talking tonight about what I think are the weirdest stars in the universe. And I've gotten asked before what criteria you really use to call a star weird. This isn't a scientific classification, it's a kind of nebulous idea. And you could really argue that any star, like the sun, is weird and unusual. And I think the more that I study stars, the more I've started to realize that there is no such thing as a normal star. But what I'm trying to do tonight is highlight the very strangest and most bizarre stars and stellar phenomena that we know about in our universe. So to start, I should take a crack at just talking about what relatively normal-looking stars are. So I'm sure some of you have seen this diagram before. For those who haven't, this is the Hertzsprung-Russell diagram. This is the diagram that astronomers use to describe, in a nutshell, the physical properties of basically any star that we observe. What we'll do is measure a star's temperature and luminosity, and we'll drop it inevitably somewhere on this diagram. So you can notice from the plot that most of the stars land along this big diagonal that stretches right across the center of the HR diagram. This is what we call the main sequence. When a star is born and starts burning hydrogen, it lands somewhere on the main sequence. You can see our sun sitting right here, right in one of the busiest parts of the busiest diagonal in the diagram. In a way, it's a great example of a very normal, average star. I like pointing out that in some ways the sun is the weirdest star that we know about in the entire universe because we're here. It's the only star we know about that is hosting intelligent life, so that certainly gives it a little bit of an edge. But what I'm trying to talk about tonight are the very most bizarre stars, and those are the stars sitting up here at the top of the diagram. These are massive stars. Our definition of that is any star that's 8 times the mass of our sun or more. So you can see the summary of what kinds of massive stars we have and how they evolved during their lifetimes. And I want to march through that briefly and highlight some examples of massive stars that you can easily find in the night sky. So when a massive star is born and starts burning hydrogen, it's sitting over here on the left. It's very hot and very bright and it's very blue. So we refer to it as a blue supergiant. A good example of that is Spica in the constellation Virgo. Spica has a surface temperature of about 22,000 Kelvin. And for comparison, our sun is about 5,800 Kelvin. So it is dramatically hotter than our sun. It's about 7 times the size of our sun. It's about 10 times as massive. So it's a great example of a sort of classic blue supergiant star. Massive stars will hang out over here for as long as they're burning hydrogen. But eventually they move on. They run out of hydrogen to burn, and they switch over to burning the next easiest thing instead, which is helium. As they do that, they start to migrate across the HR diagram. A good example of a star that's just sort of starting this process is Deneb. It's one of the big 3, one of the easy stars to find in the summer sky. This is about 8,500 Kelvin, so it's a bit hotter than our sun. It's about 20 times the mass, and it's about 200 times the size. So this is a star that's sort of starting this journey from the hot side of the HR diagram on the left to the cold side on the right. Stars actually spend an incredibly short period of time right here. They go streaking from the blue to the red so quickly that we actually refer to this as the yellow gap. Stars stick around there for maybe 100,000 years, and it's very rare to catch one there. So what kind of amazes me is that the North Star is actually a yellow supergiant. The odds of that are incredible when you really think about it. So yeah, Polaris is about the same temperature as our sun, but it started out with 8 times the mass, and it's about 46 times the size. So you can hear as I'm describing these, the sizes going up as these stars move from burning hydrogen to burning helium and crossing the top of the Hertzsprung-Russell diagram. The sort of end result of this is a star like Betelgeuse or like Antares. So this is a red supergiant. This is, again, a pretty easy star to find in the night sky, especially if you can get started on actually finding Scorpius. This star is much colder than our sun. It's about 3,400 Kelvin. Again, our sun is 5,800 Kelvin. It's about 13 times the mass, but this is what's really wild about a red supergiant. It is 700 times the size of our sun. So just to illustrate what that means, this is my little PowerPoint drawing of what Antares look like. It's a ball. So this is the size of Antares compared to some of the planet's orbits in our solar system. So if you dropped Antares where the sun is, it would eat up Earth, it would pass Mars, it would be sitting somewhere just past the orbit of Mars on the way to Jupiter. This is a pretty typical red supergiant. Betelgeuse is about the same size. So on its own, you could call something like a star that reaches out past the orbit of Mars a pretty weird star. But in reality, we have found red supergiants that are much, much bigger than this. And those are the first type of weird star that I want to talk about. To explain how we actually found them, though, I want to back up a little bit. I just described how a massive star evolves over the course of its lifetime and illustrated it on the HR diagram. When astronomers want to do this, what we actually do is trace out exactly how we think the temperature and the luminosity of a star changes during its lifetime. We'll start over on the blue supergiant side, it'll cross the yellow gap, and it'll end up as a red supergiant. By tracing out the evolution of that star during its life, we've made what we call an evolutionary track. This is the evolutionary track for a star that's 15 times the mass of our sun. We can actually assemble a series of evolutionary tracks. We can do computer simulations and estimate how stars that are 12, 15, 20, up to 40, and even higher solar masses. So what this is now is an HR diagram, but instead of illustrations of the different stars, we have simulated models of how stars of different masses evolve during their lifetimes. You see they all start over on the blue, cross the yellow gap, and wind up over here on the red side of the diagram. These are really fantastic computer models. The fact that we're even able to run them at all is amazing. But one of the hallmarks of astronomy is that we can predict things and then actually take observations to test our predictions. So we have a nice prediction here of where different massive stars should land. Particularly over here on the right, you see sort of a nice summary of where red supergiants should, according to the theory and the physics, exist. Now, if we drop on some red supergiant observations from about 15, 20 years ago, that's where they land. They don't really agree that well. You can see that they land a little too cold. They don't quite line up with that prediction of the tracks. They land in this little shaded region just to the right of where the theory predicts they should be. That shaded region is something actually called the Hayashi Forbidden region. It's named after an astronomer whose last name was Hayashi, surprise. And they basically predicted how cold a star could be while still staying stable. So when we compared models to observations, we seemed to have this really weird problem. The stars that we were observing seemed to be too cold to exist. They weren't agreeing with the physics. What we ultimately figured out was that this wasn't a problem with the computer models. It was actually a problem with how we were interpreting our observations. We were observing red supergiants and trying to guess their temperatures, but we were having a lot of trouble. To illustrate why, I can show you a spectrum of a typical red supergiant. And it looks like a mess, but it's actually almost bizarrely simple. You can see the light spread out according to wavelength. We've got the bluest light on the right, the reddest light on the left, and all the light is plotted as a function of flux, so you can see the star's really red. There's much more light over on the red side than the blue. And what you see in the spectrum is that there are these little bites taken out of it, these big, deep plunges in the spectrum. All of that light is being absorbed by molecules of titanium oxide in the atmosphere of the star. Our sun doesn't have titanium oxide in its atmosphere. Our sun is too hot. It breaks it up into titanium and oxygen. Red supergiants are actually cold enough that these molecules are able to form. And when they form, they start absorbing light at these specific wavelengths. What we learned recently is that those are actually excellent gauges of how cold the stars are. You can start with the spectrum of a relatively hot red supergiant. It's about 4,000 Kelvin. And you see those bites are, maybe just barely there. You really can't see much sign of titanium oxide. As you cool the star off, though, you can watch how that spectrum changes. The lines get bigger and bigger. By the time the star is colder, you see these enormous signatures of all the titanium oxide that is formed in the atmosphere. You can watch that change again. So we now have a really nice, neat relationship between the strengths of those lines and the temperature that the star should have. This actually was the very first astronomy research project that I ever did. I did this during the summer between my sophomore and junior year at college. Somebody had discovered that this was a great way of measuring temperatures for red supergiants, so we went out and got spectra of about 75 stars in the Milky Way. We went to Kitt Peak National Observatory. It was the first time I had ever been observing, period. I was at this amazing observatory down south of Tucson. They let me open the dome. You can't tell, but I'm freaking out with excitement there because they're letting me touch something on that board and actually open the dome with this 2-meter telescope. It was my very first time observing, and I think this might counteract the buying a telescope or eyepiece rule, because if you're a first-time observer, you have awesome beginner's luck. And we had 5 perfectly clear nights with amazing seeing, and I thought all observing worked like this, and then I went to grad school. But we got absolutely beautiful data. So the rest of my summer was spent going back and analyzing those spectra and using those titanium oxide bands to update the temperatures of these stars. So I showed you before, this is where red supergiants landed on the Hertzsprung-Russell diagram about 10, 15 years ago. And this is what happened after we finished our project. They now agree amazingly. They land exactly where we want them to, and they agree perfectly with the predictions of the models. So this was a really exciting, solid scientific result. It was exactly the sort of thing that you would write up in a paper and submit to a journal. And that was what I turned around and spent my time doing. So we have this really handy equation for how stars work that I was using a bunch when I was doing this research. It relates the luminosity of a star to the star's temperature and the star's radius. Now, we knew the luminosities of all of these stars. We had just observed them. We knew how bright they were. We knew how far away they were. We have their luminosities. We all know what 4 and pi equal. Sigma is actually another constant commonly used in thermodynamics and in these sorts of equations. We had just measured the temperature. This was our big result. And now it turned out the radius was the only thing left. So this was a pretty easy job. We solved for the radius. And now we had all the different physical properties of these stars, and we started putting them together in a big table for the paper we would be writing. This is a piece of the table that ultimately wound up in our paper. You can see all the stars' names, their temperatures, and their radii. We thought that this was the exciting column. We had fixed the temperatures of red supergiants, observations agreed with predictions, this was great, it was going to be a really cool paper. It took one of our collaborators emailing us to point out what else we had in this paper. He looked at the table and said, "You realize you've got a star in there that is 1,400 times the radius of our sun." Yeah, I think you've set a new record. I don't think anybody's ever found a star this large. And he was right. We had found the largest known star that anybody had observed. I showed you this graphic before with Antares compared to the orbits of the planets in our solar system. This is where our biggest star lands by comparison. It makes it go to the way to 7. So this got quickly earmarked as one of the weirdest stars that we knew about. This was an exciting side result of this project that we did on temperatures. It was the very first research project I did. It wound up on the CNN ticker. It was pretty surreal. But it was a really exciting result in terms of how we understand red supergiants. So we've now earmarked this star and a few companions of it, a few similarly sized stars, as some of the weirdest red supergiants that we know about. So I'll go back to the HR diagram that I showed you before. We traced out the evolution of a star from a blue supergiant across the yellow gap to what we just talked about, red supergiants. What comes next? I heard somebody say it. Supernova. Yeah. So this is the next step at the end of a star that's about 15 times the mass of our sun, turning into a red supergiant. It creates what we call a core collapse supernova. To understand why these happen is a little bit strange. I want to show you what the cross-section is of a star that's, maybe 15 solar masses and at the end of its life. This star, remember, started out burning hydrogen. When it ran out of hydrogen, it moved on to burning helium. A massive star will go on to successively use heavier and heavier elements as fuel. It'll go through carbon, neon. At the very end of a massive star's life, it burns silicon for about 3 days. That's all the time that it has to burn silicon. And these stars will keep progressing through the heavier and heavier elements that are available. And what happens is the energy of nuclear fusion in the star's core exerts an outward force that counteracts the inward force of gravity. Left to its own devices, the star would collapse. Nuclear fusion allows the star to exist. So you have this very delicate balancing act between nuclear fusion in the core and the press of gravity from the rest of the star. That balancing act works great up until you wind up with a core that's made of iron. Fusing something like silicon or helium or hydrogen produces energy. But fusing iron requires energy. It takes energy. So when this happens, that balancing act is disrupted and the whole star collapses in on itself. It still seems kind of weird that this would make a supernova. You would expect the star to just kind of go and disappear. What winds up happening is something called a reverse shock. Those layers will collapse in on themselves, and the difference in momentum and the difference in speed of the different layers causes this amazing rebound. And that's where we get the fireworks show that we see as a supernova. I actually have an animation of roughly what this looks like. So here we're zooming into the heart of a red supergiant that is starting off burning hydrogen, and you'll watch the center change color as it moves to start burning helium, and then starts moving to heavier and heavier elements. You'll watch it keep on going, you'll see a brief glimpse of silicon burning, and then at the very end, you see what happens when the balancing act loses, iron is in the core, and the star undergoes core collapse. There's that quick collapse, followed by this wonderful bounce rebound, and that gives us the fireworks show of a supernova. It's a fun, if slightly pixelated, animation. But what's really interesting is thinking about how these look on Earth. Has anyone ever been to Chaco Canyon in New Mexico? How many of you saw this? Awesome, I haven't seen it in person and I would love to. This is a cave painting in Chaco Canyon that we think is a depiction of a supernova that happened in the year 1054. You can see what we think is the daytime moon, and this little starburst just to the left of it, we think is a depiction of the 1054 supernova. This supernova was visible during the day for 2 weeks. This is how bright it got. It was recorded here. It was recorded by astronomers in Iraq, in Japan. Astronomers in China recorded it, and they actually had a name for something like this. They called it a guest star, because it visited for a while and then it left. But this was visible during the day for 2 weeks. We know a ton about this particular supernova, down to the exact date and brightness, in part because of these excellent records, and in part because we know exactly what it is now. This was the supernova that made the Crab Nebula. So we now get really gorgeous Hubble images of what was left behind, and we have accounts of what it was like to see a supernova that close to Earth. This is only about 6,500 light years away. So something like that is incredibly dramatic, and you can imagine how wild it is to see a supernova here at Earth. But the supernovae that we detect more on a daily basis at this point don't quite look like this. This is the galaxy M31, the Whirlpool galaxy, back in January of 2005. This was an example of probably two of the most nearby and most spectacular supernovae. I see a couple people smiling, so I'm sure this club must have observed this. Yeah. This is one of the most amazing examples of a nearby supernova that we know about. So you can watch as we change from January to July of 2005 and see if you can see the supernova up here. Go back again. That's it. It's this little boop. It just kind of appears in the middle of the galaxy. This is supernova 2005 CS. These are beautiful amateur images that were taken, by the way, of this galaxy at every different point. That is our signature of an entire massive star exploding and creating this enormous, bright, energetic supernova. You see it as this little tiny blip. There was another one, actually, that happened in M51 in June of 2011. You can watch the change again. 2005 CS is gone. And now, over here, we have supernova 2011 DH. I've made this point to people a lot. Astronomers have a really cool job. We get to study really beautiful, amazing things. We are awful at naming things. We have the most boring naming conventions for the telescopes, by the way, and also for what we observe ever. We name supernovae very pragmatically. They get their name from the year that they were observed in, and then we slap letters on the end to indicate which supernova it was that year. So the first supernova of 2016 will be 2016A, then we move on to B. Once we run out of the first 26, we go to AA, AB, and so on. So every time we get a new supernova, it gets a name like this. This usually works really well, and it's a great way to keep track of supernovae, but once in a while, this actually goes horribly wrong. This little fuzzball in the middle of the image is NGC 7649. It's a small star-forming galaxy that's about 78 million light years away. And back in 2009, we saw this happen. It looks really not that different than what we saw in M51. It looks like a supernova. So it got named. It got named Supernova 2009 IP. It was logged, it was noted. We thought this was yet another signature of a star dying a dramatic explosive death. It was noted, and we sat there and watched as the supernova faded away. And then this happened. The star came back. The star actually got brighter again a few months later. We've actually monitored the star over the past few years and watched it brighten and fade periodically. But this object is now stuck forever with the name Supernova 2009 IP. Even though it was not a supernova in 2009, it may even not have exploded since then. We've done observations of this star since 2009. In 2012, it actually underwent what we think was the most dramatic rebrightening we've seen for any star like this. It's still unclear whether it actually exploded for sure in 2012 or whether we just saw another temporary brightening like that. So what we think is going on is that this star is actually something called a luminous blue variable. Again, with the astronomers naming things badly, it's pretty self-explanatory. These stars are very luminous, they're very blue, and they're characterized by their extreme variability. You see them get bright and dim dramatically, and on a variety of timescales. This star was relatively fast. We saw it brightening once a year. There's a wonderful dramatic example of a luminous blue variable in the Milky Way, and it explains what we think is causing this behavior. This is Eta Carinae. It's another image that you've probably seen. It's a very famous image from Hubble. Eta Carinae is about 7,800 light years away. It's also a luminous blue variable that, rather than varying about once a year, we think that it underwent a dramatic eruption back in 1843. Our best interpretation for what these stars are doing is that they are periodically flinging off enormous amounts of mass. They're almost shuddering and hurling off mass as they go. As that happens, the star will change in brightness. We also see a change in color. We see the spectrum of the star change. Why it's doing this, we have no idea. we have a rough idea that it indicates some kind of instability in the star. You'd expect that if a star is fine, it's not flicking off mass just for the heck of it. But the mechanism that's driving it is still very much a mystery. What we do know is that they do a great job of mimicking supernovae. Some of these stars were actually originally identified as impostor supernovae before we put them all together in the same class. I mentioned that we weren't sure whether or not 09IP actually exploded in 2012. And to me, that marks this as another wonderfully weird star that we know about. Because you would really think, after the animation that I showed you and after what we understand about how stars work, you'd think that the question, did something 50 or 60 times the mass of our sun that exploded in a massive fireball that would have outshone everything in the galaxy or not, would be a fairly easy question to answer. And turns out it's a lot more complicated than that. The question of did this star fatally explode is proving very, very difficult to solve for sure, and we still don't quite have it settled. So I showed you the Crab Nebula earlier, this remnant of the supernova that happened in the year 1054. It looks from the image like the star is basically gone. It looks like all that's left behind is this leftover nebula, the outer layers of the star that have been flung off and are now being illuminated by whatever's been left behind from that explosion. It's not quite true. Somewhere in the very center of this nebula is the tiny remaining husk of the original star that we know as a neutron star. These stars get their name from what they're made of and how they work. This is what's left over from that initial collapse of the star. You can imagine as that material is collapsing in, it's going to get extraordinarily dense. What sets neutron stars apart as weird is that unlike the stars that produce them, which are supported by nuclear fusion balancing gravity, these stars counteract gravity through principles of quantum physics. The star works because of something called the Pauli exclusion principle. It basically says that two neutrons that are exactly like one another cannot occupy the same space. I think of it as like people getting onto a crowded train, and eventually they can't close the doors anymore because there's too many people on the train going, no, stop, I don't like this, I hate being this close together. It's basically that in a quantum physics form. So that's how you wind up making a neutron star. Neutron stars were actually predicted to exist for a very long time, but we didn't actually know about them until we detected a specific type called a pulsar. We know that neutron stars are very dense. We know that they have extremely strong magnetic fields. A pulsar is basically a very rapidly rotating neutron star. You can see this artist rendition here illustrating what those magnetic fields will look like. Just like on Earth, the magnetic field of a neutron star is going to be slightly off from the star's rotational axis, or the magnetic poles of the star will be slightly off from the star's rotation axis. So as you tilt the magnetic pole of the star down and beam light across it, and then spin the star, what you wind up with is a depiction of the star as flashing or pulsing. The best comparison that I've actually found is one of the emergency lights that you'll see on the top of a fire truck or a construction video. This worked better, by the way, before all these lights started getting replaced with LEDs, but you'll still see the old school type lights sometimes. These lights appear from a distance when you're driving like they're flashing at you. This is what's actually happening. You have something rotating inside the emergency light shooting a beam in two different directions. So you get the impression of flashing when what's actually happening is this beamed rapid rotation. So I don't know, the next time you're driving and you see a construction vehicle or a fire truck or something that's flashing these lights, you can remember that that's basic, pull over, and then remember that that's basically what's happening inside of a neutron star. Something else fun that's worth remembering is that that's pretty much the speed that a lot of pulsars are moving at. Pulsars are really small by the scale of most stars. They are about the size of the city of Denver, but they are so dense that if you took 1 teaspoon of them, they would weigh more than Mount Everest. So this gives you a sense of scale for what these stars are like. Even something the size of the city of Denver is pretty large, and it's pretty much spinning at that speed or much faster. That's a relatively slow pulsar. There's something kind of funny, by the way, about how pulsars were discovered. These were detected in the 1960s through their radio signatures. Jocelyn Bell is the person popularly credited with discovering pulsars. While she was observing, she noticed a radio signal that was basically doing this. At the time, they didn't immediately have an explanation for what this could be. Neutron stars were predicted, but it would take a little while to put them together. The observers actually detected 4 of these in the initial early days of doing these observations, and they nicknamed them LGM 1, 2, 3, and 4. Yeah, LGM stood for Little Green Men. They were mostly kidding, but it did occur to somebody that such a regular and perfect signal could potentially be coming from an artificial source. Of course, something rotating very rapidly is a much more comfortable explanation, but it's still sort of a fun story for where the naming convention came from. Yeah. So we've talked about neutron stars, these stars that fight against the inevitable press of gravity with neutron degeneracy pressure, this principle of quantum physics. That works really well until the neutron star gets up to about 2 times the mass of the sun. And then even quantum physics cannot counteract what's happening. And we move from a neutron star to a black hole. So I've been showing you lots of really cool artists' renditions, and where we have them, observations. Black holes, kind of. Like, we don't quite have the beautiful pictures of what black holes should look like. Thanks to the movie Interstellar, we now have some really awesome fake pictures. But it at least gives us a rough idea of, for example, what a black hole would do to the light around it. Black holes are absolutely mind-bending. They're fascinating objects. What I always found interesting about them and what got me into astronomy when I was a really little kid was this idea of how black holes were actually made. That you could go from a relatively normal-looking star to something that completely stretches the limits of how we understand space and time. Believe it or not, black holes are made pretty regularly in a supernova without a whole lot of fanfare. A supernova might make a neutron star that then becomes a black hole. A more massive supernova might go straight to a black hole. On their own, these are relatively typical of supernovae and not particularly remarkable and not particularly weird. What marks black holes as weird are a subset of the events that make them. Sometimes, instead of just producing a normal supernova, you get a supernova accompanied by what's known as a gamma ray burst. We still don't have a great idea of where gamma ray bursts come from, but I can give you a rough animation of what we think is happening. This animation will start with a star that again is very massive, in this case more massive than the one we saw before, a star that has shed its outer layer, so instead of looking red it now looks blue again, and a star that is about to have its core collapse directly into a black hole. What we think happens to make a gamma ray burst is that this star with its core collapsing will be rotating very, very rapidly. When that rotating core collapses, it will start to devour this star from the inside. It ignites these incredibly energetic jets punching out of the star at opposite ends. This is what's being caused by the black hole consuming the star from the inside as it rotates incredibly rapidly. The star eventually either diffuses or is swallowed. Collisions in those jets emit gamma rays, which we see as a gamma ray burst, and eventually whatever remains produces the supernova explosion that we're used to seeing from a normal stellar death. I want to run this again and point something out. This star, we think, has to be at least 30 times the mass of our sun when it's born. This video is happening about in real time. Those jets that you can see stick around in this video for maybe 25 seconds. That's how long a typical gamma ray burst lasts. They can be as short as 2 seconds. They can be as long as several thousand. But they're incredibly fleeting events. They're signatures of these very bizarre, very weird stellar deaths, but they're pretty hard to observe if they only last that long. And this gets into how gamma ray bursts were actually discovered. This is an artist's rendition of the Vela nuclear test detection satellites that were launched back in 1967. Their job was to actually point at the Earth. They were supposed to monitor the Earth for a flash of gamma ray emission that would indicate that someone had violated the nuclear test ban treaty and set off a nuclear test. The satellites worked great. They detected gamma rays from all over the place. And fortunately for the peace and happiness of all mankind, none of them, at least none of them that we've been told about, came from Earth. Instead, what we ultimately determined once the research was declassified like 5 years later, was that these flashes were coming from all over the sky. We had a bunch of different ideas for what these could possibly be. Again, the concept of interstellar space battles was floated at some point. And it wasn't actually until 1998 that we associated these with a dying star and with a supernova in a nearby galaxy. This is still, by the way, the most nearby gamma ray burst that we've ever seen. It's about 40 megaparsecs away. But this was our hint as to what was actually causing these and the fact that they came from massive stars. So the Vela test satellites worked sort of by serendipity. We now have satellites specifically designed to detect and study these very brief flashes of gamma rays that we get from dying stars. And this is a great example of one of them. This is the SWIFT gamma ray satellite that NASA launched back in 2004. You can see that it has this big flat panel on the front. That entire panel is used to detect gamma rays. It has basically a baseball cap over the top, a sun shield, protecting an X-ray telescope and an optical telescope as well to do follow-up observations whenever this detects gamma ray emission. What this will do is orbit the globe and monitor a large piece of the sky and wait for a gamma ray burst to happen. When one does, the telescope will very rapidly slew and try to center that gamma ray burst as best as it can. It basically goes, oh wait, oh my god, points to that part of the sky and looks for light in other areas of the spectrum, X-ray light and optical light, that can localize this burst as much as possible. Whenever a gamma ray burst is detected, this data is then transmitted down to Earth, and observations kick off trying to study the galaxy that this happened in as close as possible, trying to study the optical or infrared or radio light of the burst, and basically trying to get as much information about it as possible. The kind of astronomy that I've been describing, supernovae that happen and then fade, or luminous blue variables that we see turning off and on, or a gamma ray burst that only lasts a few seconds, are all subtype, or they're subfields of what we call time domain astronomy. It's astronomy that operates really on a human timescale, which is pretty impressive when you think about it. What I like pointing out sometimes is the difference between how people might think time domain astronomy works, like time domain astronomy the movie, and then how time domain astronomy actually works. So you imagine something like SWIFT detecting a new gamma ray burst, localizing it, and passing that information down to Earth. You imagine that like the science siren goes off. So some massive alert goes out to all astronomers. We have found a new gamma ray burst. This is incredibly exciting. Go do your thing. The public tends to picture professional astronomers as doing this. I've had people ask me, do you have your own telescope in your backyard? Is that what you do your research for? I do have a telescope and I love it, but it's not how we say study gamma ray bursts. But you still get this mental image of an old man in a lab coat for unclear reasons, staring through the bottom of a giant telescope in a dome somewhere with paper scattered around because scientists. You imagine that the data comes back that looks something like this. You get this beautiful, dramatic, absolutely immediately in color image of an exploding star.
I knew it.
Huh?
I knew it. That's how it was.
That's how it all looks every time. Yeah. And it looks beautiful and dramatic, and it tells you something about the fate of the world, and you like call the president. And then it ends with you saving the world because of a supernova. And I think that was like most of the plot of Deep Impact right there. The reality of this is, I still think really exciting, but a little bit different. When a gamma ray burst is detected, there isn't a mass science siren. Most of us find out like this. There are now text alerts or various app alerts that let you know when a supernova that fits specific criteria or a gamma ray burst has happened. This used to be done by beeper. We've now moved on to doing it by smartphone. I personally think the telescope part of this is cooler. We get to use something like the Keck telescopes on Mauna Kea, but you don't necessarily get to run to them immediately. In some cases you do. There's telescopes that have what they call targeted opportunity programs set up. When a targeted opportunity, like a new gamma ray burst, is triggered, that telescope will get a notification, and the observer will get a notification saying, please stop whatever you're doing at your earliest convenience and point at this thing. It just happened, it's time sensitive, we want to get data on it before it's gone away. I've actually been at the Keck telescopes when we got a gamma ray burst call like this. Other times, you just know where it is and then apply for time and wait. You'll typically apply for time and get a night, maybe 2 nights allocated to you in an entire year, and you'll fly down to Hawaii, observe, and that's, in a lot of cases, the quickest turnaround that you can get to observe something relatively time sensitive. I want to highlight, by the way, just how big the Keck telescopes are. We know that they're 10-meter mirrors, but for scale of that entire building, that's a guy. And then there's one of the 2 twin Keck domes. It would be really cool if we actually went into this dome and observed, but for something like Keck, we aren't even in the telescope, we aren't even on the mountain. We are down at sea level at a headquarters that communicates remotely with the mountain. So this is what my workstation looks like on a typical Keck observing night. And I can clarify what a lot of what you're seeing. You have mechanical information about the telescope, you have finder charts and night log to keep track of what you've looked at. The data itself, which I think you can tell just from an image of the screen that it's maybe not the gorgeous image that the public likes to pretend. We're keeping track of the status of the telescope, the status of the weather. I'm taking notes on my laptop while this is going on. The operator, the person actually running the telescope, is here. My arrow is pointing to a remote control that controls a conferencing package and software and a big screen that has me talking directly to the operator up on the mountain. But we are in completely different parts of the big island of Hawaii. And finally, a crucial element of an observing run at Keck is your Kindle. Because you hope that your Keck night looks like this. You hope that this is the weather you're getting every time. But sometimes, after applying for a night or 2 at Keck and flying down and allocating that 1 or 2 nights as your only chance to get data on this object, sometimes you go down there and the weather looks like this. That's a real picture that I took at Keck. You're sitting in building 1 and trying to see building 2. So you saw how big the building is. And when you can't see a 10-story building 30 yards away, trying to see a gamma ray burst that just exploded many megaparsecs away is not going to go very well. But it happens. We can get around the weather by moving on to something like Hubble. We at least get to avoid problems such as clouds or other earthbound issues. Kind of similar to observing on something like Keck, you have to apply for Keck time. You have to apply for Hubble time. Hubble gives out time in orbits, so you'll get a handful of Hubble orbits and get your data that way. Hubble, as you've seen, creates absolutely beautiful data. Hubble is even more competitive, but again, we skip the problem of clouds. As long as you don't have a mechanical problem, which only happens occasionally, Hubble is a pretty reliable telescope, you do get a chance to get better data this way. But whatever the data is, it'll come down, and a lot of times it looks like this. This is some of the raw data that I got from Keck. And this is the problem. You're looking at it going, oh, I know, but you can still see what you're looking for. No. That's the object you're actually looking at. You can barely tell that it's there. It's this little tiny bright blip. So there's a lot of data processing and data analysis that needs to be done. You can significantly improve an image like this. You know what the sky is going to contribute. You can take away the sky. You know what the heat of the Earth is going to contribute. You can improve on this dramatically, and you do eventually get data that you want to share. Instead of calling the president, you wind up writing a paper, or in the case of gamma ray burst, posting on something called the Gamma Ray Burst Circulars Network. This is a website that updates automatically with news on whatever the latest observation of a gamma ray burst has been. Sometimes this is a swift detection, sometimes it's a ground-based observation that gives you a distance to the object or even just a better location, but it's one of the best resources that we have for studying gamma ray bursts, and it updates very, very quickly. This is another good example. It's called the Astronomer's Telegram. It's a website, so this should give you an example of how long this has been around. But these are our updates on supernovae, or variable stars, or smaller novae. Any variable star behavior that has happened will get updated to something like the Astronomer's Telegram website. So this is how we post new updates and tell each other about new events in something like time-domain astronomy. The last thing I want to mention before moving on to the last piece of my talk is, I showed this image earlier. I showed this depiction of what that supernova from 1054 looked like from Chaco Canyon in New Mexico. That was one of 3 galactic supernovae that happened in kind of rapid succession early in this past 1,000 years. We had a supernova in 1054, one in 1572, and one in 1604, and we haven't had one in the Milky Way since. We can actually roughly guess how often a supernova like this should happen in our Milky Way. We have a guess at how fast we're making new stars, we have a guess at how massive the stars are, and we can get a rough idea of how often one of those stars should die. And according to the statistics, we are overdue. So I love doing this thought experiment of what would happen if we all left here tonight and started getting in our cars and driving home, and a galactic supernova happened that we could see. Again, it would be so bright that it would be visible during the daytime sky for 2 weeks. Honestly, at first it would probably freak people out. If you see an object in the sky that's slowly getting brighter and brighter and you're not quite sure what's going on, you could have some really pessimistic ideas about what could be causing what you're seeing. Once we knew for sure that it was a supernova, it would absolutely become the most talked about astronomy event that we have seen. Imagine every day in the middle of the day you would see the sun and then this supernova. They would be making jokes about it on The Daily Show. It would have a hashtag. It would be trending on all of the social media that anybody uses anywhere. It would be the first supernova that had happened since modern astronomy, so every astronomer would just collectively lose their minds. And those scrambles to use every possible telescope would just ratchet up to top speed. It's fun to think about, and I really do hope that something like this happens. For the most part, any of these supernovae will be happening so far away that we will get an amazing fireworks show, but Earth won't be threatened at all. We don't have anything to worry about in terms of a supernova happening so close that it would violently disrupt life on Earth. We would mostly just get that view that we saw depicted on the cave wall of this new bright star sitting in the daytime sky for 2 weeks. Yeah.
What's the approximate average rate that we should see galactic supernovae?
I think the guess was about 1 every 100 years.
Wow.
It's very approximate.
Of course.
But yeah, the last one was in 1604.
The number of sample points is small.
Yeah. The number of sample points is small, and this is actually easier to estimate for a galaxy that isn't our Milky Way. When we can see the whole galaxy, it's much easier to get a rough estimate of how fast it's making stars. Something like the Milky Way, where there's parts we can't see because the Earth's in the way and there's all sorts of other problems, it's harder to guess, but roughly 1 every 100 years. So I talked about a good collection of weird stars tonight. I talked about red supergiants, I talked about core collapse supernovae and gamma ray bursts. I talked about these neutron stars that are supported by quantum physics rather than the nuclear fusion that we think that supports normal stars. I've pretty much covered the weirdest types of stars that we can possibly imagine. And the only way to make them weirder at this point is to take 2 of them, like, say, a red supergiant and a neutron star, and to combine them. So I started working on red supergiants back in 2004, and I've been working on them since then in one form or another. My collaborators and I started writing papers on them. We started becoming some of the people that others would come to with questions about red supergiants or ideas about them. And one day in about 2009, we got an email from a woman named Thorne-Zytkow. And her email started off like this. As she described it years ago, herself and Kip Thorne invented theoretical models of stars. So if you know who Kip Thorne is, he's this astonishingly talented theoretical astrophysicist. He's the guy behind the science in Interstellar. And when someone starts their email with Kip Thorne and I invented types of stars, you go, okay, and you listen to whatever they say. She went on to describe these very fascinating types of stars that were similar to red supergiants and asked us if we were interested in looking for them. The stars were named after her and Kip Thorne. They're referred to as Thorne-Zytkow Objects, again with the not so creative with the naming, but in this case, the scientists that conceived of them do at least get credit every time the star is talked about. So Thorne-Zytkow Objects, or TZOs, are a theoretical class of star where we have a neutron star core that's surrounded by a big, puffy envelope. It's a wild idea because we think that anything that looks like a normal star should be supported by nuclear fusion. This is a model that takes the quantum physics supporting a neutron star and drops it in the middle of an otherwise normal-looking star. It gives us a completely new way to make a normal star, the kind of star that you would plot on the Hertzsprung-Russell diagram. We have ideas for how you could make a star like this, and the two most popular ideas are predicated on the idea of massive stars and binaries. Binary systems were mentioned briefly before. You've basically got two stars orbiting one another, two stars that are gravitationally bound. The way that we imagine making a Thorne-Zytkow object requires that we have two massive stars in a binary. In the first idea, you have a massive star that undergoes core collapse, dies, makes a supernova, and leaves behind a neutron star. That star's companion is still around, and the two stars are still gravitationally bound. That companion will then start to evolve across the HR diagram from the blue side to the red side, and as it does that, it'll grow. It'll start to get enormous like those red supergiants that we discovered earlier. As it gets that large, it swallows the companion neutron star, and the neutron star goes spiraling into the center of the star and eventually settles at the core and eventually supplants the star's original core. This is one way to basically make a star with the neutron star for a core. Another way is a little funnier, but also actually statistically pretty likely. In this case, you have two stars in a binary. One is already a red supergiant, and one is about ready to go supernova. When that second star goes supernova and produces a neutron star, it doesn't just create this sort of perfect boom and leave a neutron star directly where the star was. Most of these explosions are a little bit asymmetrical, so the neutron star will go flying off in a particular direction. If the neutron star is kicked in the right direction, it'll actually go flying right into that red supergiant companion star that is sitting and waiting for it. So we wind up firing a neutron star directly into the core of a neighboring red supergiant. It sounds totally ridiculous. It sounds like you need a supernova with really awesome heat. But in reality, red supergiants are so big, and the two stars would be so close together, that it would be subtending a pretty big area of the sky. It would be almost hard to miss if the neutron star was heading anywhere in that general direction. So these are two different ways of getting a neutron star inside a red supergiant and making what we think should be a Thorne-Zytkow object. I need to be honest about the little artist rendition that I showed you before. We talked about the sizes of these before. The red supergiant is the size of the orbit of Jupiter or more. The neutron star is the size of the city of Denver. So when you actually combine them, the neutron star is utterly invisible. In fact, from the outside, these stars should look exactly like red supergiants. So they were predicted back in the 1970s, but for 40 years they existed purely as theoretical stars. Nobody had ever found one. Finding them is difficult since they look exactly like red supergiants, but it's not impossible. They look almost like red supergiants, and to understand why, we need to talk about what's going on in the star's interior. This is again a little PowerPoint drawing of a cross-section of a red supergiant. You have the star's surface, you have that core that's burning helium, and you have the envelope in between the two, which has a bunch of large convective cells going on inside. In a Thorne-Zytkow object, it's almost the same. You have a TZO surface, you have that neutron star for a core, and the kicker here is that that envelope is completely convective. It's not just one giant cell, like I've drawn here because of my limited PowerPoint skills, but there's a giant pile of convection that is connecting the surface directly to what's going on near the base of the star, is what we call the envelope, and near the surface of the neutron star. This actually allows a really bizarre chemical process. What happens is that you have material in that convective envelope that's getting dragged around and around the star. Down in this little region near the neutron star core, everything is incredibly hot and everything is incredibly dense. In a condition like that, you actually have protons that will get very rapidly shoved onto the material that's being dragged past. So every atom that gets pulled past that neutron star core is getting bombarded with protons. When you add protons to elements, they start moving up the periodic table. So you're making new elements as a result of this. Before you can get as far as you can get by adding protons, just get to the chemical limit, that material actually gets dragged back out into the star, and it starts undergoing what we call beta decay. It emits electrons or positrons and eventually winds up drifting back to elements that are slightly lower on the periodic table. We repeat this process over and over, and it's a process that can only happen in a Thorne-Zytkow object. You can only do it if you have this big convective envelope connecting the surface of a star to that hot burning region right near the neutron star. What eventually happens is that you get really bizarre elements at the star's surface. You get things like molybdenum and lithium and rubidium. These are elements that you would never normally expect to see in a red supergiant. So these elements are the only way that we can tell the difference between a red supergiant and a Thorne-Zytkow object. We would see excess molybdenum, for example. That's the only sign that we have. The problem is that these elements are rare in stars, period. So actually getting the data to figure out if you have a red supergiant with a lot of extra molybdenum is really difficult. When Anna Zytkow emailed us, we agreed to kick off an observational campaign to look for Thorne-Zytkow objects. We took all the red supergiants that we had observed, and at that point we had observed red supergiants in the Milky Way and in the Magellanic Clouds in the southern hemisphere. We collected the ones that we thought were most likely to be Thorne-Zytkow objects, the brightest, the coldest, the reddest, the most compelling stars, and we went back and re-observed them with the Apache Point telescope, the 3.5 meter in New Mexico, and the 6.5 meter Magellan Clay telescope down in Chile. I showed you an example of a red supergiant spectrum before, and this is a nice, moderate resolution spectrum of a star. We had to go to much higher resolution. We basically had to zoom in on little tiny pieces of the spectrum and look at every tiny little bump and wiggle. We had to identify the teeny little blip that was caused by lithium or by molybdenum. And we had to do that for every single star. Nobody has a good sense of how much molybdenum is in a normal red supergiant. So we had to do this for everything we observed and see if any of those stars stuck out as unusual. So these are the three elements that we looked at. You see that molybdenum absorption blip. You can barely see that. That's light that we think is being absorbed by atomic molybdenum. It's barely visible at all. There's lithium, there's rubidium. This is what all of our stars looked like. They all looked something like this. The lines were about this strong. This was similar to when we found that new record-setting largest star. We thought this was the result. We thought we were done. We thought we had a really nice paper saying, if anybody wants to look for a Thorne-Zytkow object, we know how much of each of these elements is in a normal red supergiant, so you can use this as a starting point. What absolutely amazed us at the time is that we had one star in our sample that looked like this.
Wow.
You can compare the strengths of the two lines. This is molybdenum in a normal red supergiant. This is molybdenum in one of the stars in our sample. You can see the same for that lithium line and for the rubidium line. All the lines around it, by the way, are the same. Those were lines of elements like nickel and iron that aren't enhanced in a Thorne-Zytkow object. In this star, we had actually found the first candidate for the observational detection of a Thorne-Zytkow object. It sounds more dramatic than it is. You see this little tiny blip, and the blip got bigger, and you do that a few times until you're convinced, and then that is our potential discovery of a Thorne-Zytkow object. The existence of these stars would have unbelievable implications for stellar astronomy. We could, in that spectrum, have evidence for a completely new way of making stars. We could have evidence for what happens to binary stars at the ends of their lives. This gets really important when we try to figure out how fast stars are made or how many stars are made. Those elements that I pointed out, the fact that we're getting extra molybdenum or extra lithium, is really important for figuring out how the universe evolved chemically. Something like lithium is a really important ingredient in understanding the evolution of the early universe. If we have a new way to make it, that completely changes some of our chemical equations for how the universe became what it is today. So this would be completely amazing. And this is why I sometimes point out, I think Carl Sagan is credited with the quote, so it's the Sagan standard. Extraordinary claims require extraordinary evidence. Saying that we have discovered a Thorne-Zytkow object is an extraordinary claim. Our evidence is three little lines. that are stronger than the other lines. It's very compelling, it's very scientifically sound, but it's still not enough. It's why whenever we wrote about this discovery, we were really careful to call what we had found a candidate. It is by far the weirdest possible star anyone could imagine or anyone could discover, and we think that we found one. But this is really step one of the science. This is, again, the movie versus reality science. We have many more observations that we want to take. There are new computer models that are already being run of Thorne-Zytkow objects to try and figure out how they should look exactly. And there's a lot more exciting work to be done on, again, what I think really are the weirdest stars that we could possibly know about. So on that note, I want to go back to my title slide, and I'm happy to take any questions that you might have for me. Thank you very much.
In your equation, you had a luminosity. How are you so sure of the luminosity of the stars that you're looking at?
In those particular cases, we have the magnitude of the star, the visual magnitude in those cases, and some of the infrared magnitudes very, very precisely. We know the distance to the stars because they're in known associations of massive stars. Massive stars kind of get made in big piles, so we have a very precise distance to the cluster of stars that that specific star is in. And knowing the temperature is also important. If a star is incredibly cold, most of its light will be emitted in the infrared. So if we're observing it in the visual, we're missing some of the light. The same for if a star is really hot. It'll emit most of its light in the ultraviolet, and you miss some of it in the visual. So if you know its temperature, you know its black body spectrum, you know where it'll be emitting the most light, and you can correct your magnitude to really account for the total luminosity that the stars emit. So in those cases, we know it pretty accurately. Yes?
How long do the stars spend in the yellow gap?
Sorry?
How long does the star spend in the yellow gap?
The expected, something like 100,000 years. Astronomers, we put really big error bars on things, so that could be off by some amount, but it's a fleeting amount of time for a star. It's a very short-lived phase. What's interesting is stars will cross from the blue to the red and spend some time in the yellow gap. Some stars actually then cross back. They turn from red supergiants to something called a Wolf-Rayet star. And they again pass through the yellow gap and appear as red supergiants. Something that is kind of an open question right now is how to tell which direction a yellow supergiant is going, because it's not totally obvious whether it's on its way to being a red supergiant or coming from being one. Yeah?
I have a couple questions. In your early research on the table, there was a reversal of energy output. Kind of at the beginning, it was like almost a Z.
Okay.
In the graph. What does that represent? What does that change?
Oh yeah, the little Z right at the left-hand edge. I have no idea. Don't know. What it probably has something to do with is the transition from burning hydrogen to burning helium. In lower mass stars, you get something called the helium flash, which has to do with that switchover, and you see it manifested in how the star moves on the HR diagram.
Can you show that slide again?
Yeah, I can go back to the beginning slide. Maybe I can find my mouse. Here we go. I believe that what you're asking about,
The tracks, yeah.
is this.
Yeah.
Yeah. In terms of what exactly is causing it, it's expected that it has something to do with the transition. If I'm remembering correctly, that little Z is driving the group that runs these computer models absolutely crazy. These are very computationally intensive. They take a really long time to run, and getting that accurate, or even getting that such that the physics still obeys laws of physics, takes a while.
Okay, so when you're seeing the proliferation of the light-absorbing elements, could you apply that to what you're seeing with like the blue fluctuating stars, to where maybe you're getting larger fluctuations and maybe applying them to this little switchback pattern, so where it's not necessarily happening again.
Yeah, I can use this actually. You possibly could. That would be a nice way of diagnosing where a star is in its evolution. This actually comes back to the question I was asked about how well we know the luminosities. We know the luminosities pretty well, and we know the temperatures pretty well. That is an extreme level of detail, and we're not quite there. And what would happen is, honestly, we need to be there with a pretty large collection of stars, and massive stars are just rarer than stars like our sun. It's when you make a bunch of stars out of a cloud of gas and dust, you make tons of little stars and a few big ones, and just as a consequence of that, we have a limit on how many stars are nearby that we can observe. I don't know if anybody's really dug into trying to drop stars around that exact Z shape. I suspect people have, but in terms of how precise it is and how well we can test the models, it's still developing.
What are some of the implications of these stars that have other different elemental composition on the possibility of what planets might be composed of, supernovas that are made up of the supernova remnants from those stars?
It's an extremely interesting question. We know so little about them that it's hard to answer what the impact might be. Something like enhancing lithium is very interesting because our basic understanding is that lithium started getting made in a very, very early universe. So the lithium content of the universe is a really valuable diagnostic for how things went basically soon after the Big Bang. If we've got a new way to introduce lithium to the system, it adjusts that equation accordingly. In terms of something like what planets are made of, and whether rubidium or molybdenum are contributing to that, that then gets into the question of what happens to a Thorne-Zytkow object when it dies. And we really don't know yet. We know that you have that neutron star and the big envelope, but we don't know what the end game is for that star. It's possible that the star could blow itself apart, and that envelope could eventually puff off and leave behind a naked neutron star, in which case all those elements would get flung into the interstellar medium, and they would become building blocks for things like new stars and eventually planets. There's another scenario in which that neutron star exceeds the mass limit to become a black hole, and the whole star just goes shh and disappears. We do think that there are stars that do this. Stars that go directly to a black hole could just vanish. We actually might have observational evidence of something like that happening. And in that case, they make very little contribution. Not none. Some of that mass will still get blown off, but the contribution is much less. And if the star does explode as a supernova for some reason, then those elements collide with protons and electrons in the interstellar medium and become heavier elements. So what it does to the chemistry really depends on how we think the stars die and on how long we think they live, which we're also not certain about. Yes?
On that chart there, you've got 32 solar mass stars and 40 mass stars, which looks like they go back and forth, do they? Really?
Yes. Yes.
Those are ambivalent stars.
these are examples of what I mentioned.
Where on the gap they are.
We can't tell where on the gap they are. When this star will start as a blue supergiant, cross the yellow gap, and become a red supergiant. When it's here, we can't really tell where it is. But when the star stops being a red supergiant and turns blue again, it actually looks very different than a blue supergiant. It's a whole different class of star that I didn't get a chance to talk about, even though they're legitimately weird. They're called Wolf-Rayet stars. They don't have a hydrogen. Yeah, they don't have a hydrogen envelope. All the hydrogen's been blown off. That little cross section that I showed, the hydrogen's gone. Sometimes the helium envelope is gone, and most of what you see are elements like carbon and nitrogen. They're also incredibly hot. So we know that those stars have undergone something like a red supergiant phase and lost the mass.
So how much of the mass is left after?
Not a lot in some cases.
Yeah, I was going to say.
It depends.
Obviously, it wouldn't be 32 solar masses.
No, those are all the masses of the stars when they're born.
Okay.
By the time they die, we have a tendency to refer to a star by the mass that we think it was born with.
Okay.
By the time they die, there are 5 solar masses, maybe even less. But this is probably the most interesting question in stellar astronomy right now, is how stars lose mass. What actually makes them lose mass? Whether they shudder and throw it off like a luminous blue variable, whether they lose mass through something we call stellar winds, which is basically a photon version of wind in a room, that same idea of a pressure differential carrying mass away. If a star is in a binary, and those two stars are interacting and one is pulling mass off the other, that's a whole other way to lose mass.
Yeah, do it.
And it's like there are week-long conferences where all we talk about is mass loss on stars.
Right.
Yeah.
The secular limit for applied work is like 1.4 solar masses, is that right? If it gets
It's
bigger-
supposed to be, yes.
Well, that's a theoretical
It is.
number, it's a little bit hard.
Mhm.
And I think that you said the mass for a neutron star is about 2 solar masses, that's for the neutron star itself.
Mhm.
And when it grows bigger than that, then it implodes into a black hole.
Yeah.
It's where
The two numbers don't match, and that's a problem.
Well, but
We found neutron stars that are 2 solar masses. I think the record right now is 2.2, if I'm remembering correctly.
Okay.
And that puzzles people very much, because according to how we understand physics, that shouldn't be able to happen. It should have made a black hole.
Shouldn't be able to get that big.
So these are, I'm not sure if the explanation is that there are necessary tweaks to quantum physics, or if there are other things that we don't understand about the star, but the fact that we found neutron stars that massive is puzzling and surprising.
Or again, possibly observational refinement is in order.
They've been very, very careful about measuring these masses, I know that for sure. When you find a result like this is something I find funny about science in general. I think the first time someone measured a neutron star mass and found it above 1.4, the first thing they did is, oh my god, I screwed up. What did I do? There's no way. And you check yourself absolutely to death before you state anything like that.
Of course.
Yes?
I have a two-part question. One has to do with the forming of the neutron star. Is that the gamma ray burst? That's perpendicular from its spin and rotation, right? It comes out perpendicular to that. So
No, it actually comes out, we think that a gamma ray burst comes out along the rotation axis. Something like a pulsar or a neutron star, what you're seeing is a beam of light along the magnetic poles, which will be, it could be perpendicular. More likely it's just offset by a certain angle, similar to how the magnetic poles are offset from the geographical poles on Earth.
but that gamma ray burst is, kind of unidirectional.
Yes, it's very unidirectional.
The detectors, what are they picking up? Are they picking up the gamma ray burst, or is it like a portion of? What are the ramifications of a direct, head-on bullseye gamma ray burst?
We're only getting the bullseyes. The light is so what's happening is you're getting this jet shooting out along the rotational axes of the star. The rotational axes of that rotating black hole in the inside. Collisions of material in that jet are what emit the gamma rays, but it's only emitted across this very tight beam. So if a gamma ray burst is pointed right at Earth, SWIFT will detect it. If a star explodes and the jets are pointed this way, we will never see it. There's actually been observations of what we think are off-axis gamma ray bursts, where we see a star that died and shot a gamma ray burst, but we couldn't possibly have seen it. And identifying something that isn't there can be really hard. But what we try to do is basically say, well, that supernova very closely resembles the supernova of something that had a gamma ray burst, so we think they might be the same phenomenon. But we miss them if they're not pointed at us. We think that we only get about 1 in every 300. Yes? Yep.
Is there a theoretical limit to both the mass and the absolute diameter of these massive stars?
Massive stars in general?
Any star?
Yes. The absolute diameter is probably easier to answer. I just don't know the answer off the top of my head. But there should be a limit, and it's somewhat, believe it or not, it's actually somewhat based on the galaxy where a star is born, because it depends on the star's chemical makeup. But there is a limit to how big a star is allowed to be and how cold a star is allowed to be before it just is not able to remain stable. In terms of how massive a star can be, this is something that's a bit debated in the astronomical community. I'm showing some of the evolutionary tracks right here. The group that made these models kept going. They went up to 120 as the most massive star, so 120 times the mass of the sun. The predictions are that stars could get more massive than this, that you could see 200 or 300 solar mass stars. Those are predicted, we've never observed them. It's possible that we can only observe that those are only producible in something like the very early universe, where the chemical makeup of the universe is very different. And there are ideas that the stars could keep going further and further. People love to theoretically make a star that's 1 million solar masses and just see what it would do, but it's unclear whether or not you could actually make something like that.
So as a practicality, we think 120 solar masses?
120 is the most that we usually model. People that specifically study this will go up to about 300.
And what kind of a diameter would a 120 solar mass star have?
Believe it or not that big. 120 solar mass star is actually so hot and so massive that it would never become a red supergiant. There's a weird limit just above where this diagram stops, where stars stop turning that cool. They just stick around on the blue side. And to get really massive, the stars have to be very cold. So they'll be big, but they wouldn't be as big as that star that we found that reached out to the orbit of Saturn
So
almost.
theoretically, there could be a star even bigger than the one that you found.
Yes. It could be bigger, but it wouldn't be because it was 120 solar masses. It would be because it was very bright and also very cold.
One final thing. Is it possible if there's one of these red supergiants with a single neutron star in the middle, could there be a binary neutron star in the middle?
No one's ever asked me that. That's really interesting. I don't see any reason why not. But that could affect how long that star lives. Two binary neutron stars that are very close and orbiting each other very rapidly is an incredibly violent system. Two stars doing that actually eventually collide, and those make a completely different type of gamma ray burst. We have two types of gamma ray burst. We have long, which are the kinds that I talked about, and short, which last a second or half a second. And we think that those come from colliding neutron stars. So there's no reason in theory that you couldn't put one inside a red supergiant and have that happen, but it probably wouldn't live very long. And we also wouldn't be able to use our trick of a star that collapses and goes flying into a neutron star to make one. So I think forming one would be hard, but I don't think it would be impossible. I think it wouldn't look like a Thorne-Zytkow object. Yes.
This is just kind of.
Sorry, there was one in the back.
This is actually kind of mundane and practical, sort of. You said you have to fly to Hawaii and you don't actually go into the scope. You're in a remote viewing area. Why can't that be done from all over the world?
Caltech has a remote observing area for Keck that Caltech astronomers use. I believe that sometimes astronomers could just fly there if they desperately need to, but there is an advantage to being on the island in terms of communication efficiency, in terms of data efficiency, and that, by the way, is Keck alone. There's lots of other telescopes on Mauna Kea that you have to physically be at. The Subaru telescope, for example, you go all the way up to 13,000 feet and sit in the telescope.
It just seems to me that it would expand the number of people that could be looking for things if we had distributed access to it.
Believe it or not, that's not the limiting factor is the number of nights. If somebody needs to go to Keck or observe remotely from Keck on that New Mexico telescope, for example, 3.5 meter, I could be observing on that right now. I could be observing on that from my living room, and I have. Something like Keck, it's beneficial to be there, but the limit isn't where you can be while you're observing, it's whose night it is. Every single night on Keck is given to somebody for the most part, or it's dedicated to engineering work. Same for every other telescope, so that's how we limit how many people can observe.
But no one else can look at the data while it's going on?
Not while it's going on, but some of the data is made immediately public. There is Hubble data. There's a whole class of observations that Hubble takes, where as soon as the data is taken and downloaded, it is publicly available, and anybody can look at it. I had Hubble observations about 1.5 years ago to observe ultraviolet light from galaxies that are making these kinds of massive stars. And because of the nature of the observations, as soon as the data was taken and arrived on Earth, anyone could look at it. I'll be honest, when you look at it, it looks like an enormous mess because it's completely raw and not reduced. But there are lots of telescopes whose data becomes immediately publicly available. And for something like, I think I'm getting this right, for something like Keck, and certainly for something like Gemini, data becomes public after something like 1 year. Or in Hubble, I think it's like something after 18 months. So in those cases, the astronomer that writes the proposal and earns the time and takes the data gets a little bit of a head start, but eventually that data is available to anybody. So there are huge archives of publicly available data out there.
This is just kind of a comment. The Denver Astronomical Society has a link to this whole process that many of you may not know about. It's been around for so long. The first picture of the gamma ray burster was actually found by a guy named Dr. Bradley Schaefer. Does that mean anything to anybody here? Okay.
Was that 98 BW?
Oh, I don't.
Hang on, I'll have to find the
exactly
pictures.
what the
The picture was a
It
drop.
was found in a series of plates in the stacks. I think it was 1926, taken in South Africa. It was a series of 6 frames taken. The number 5 was the discovery plate of the first gamma ray burster. It wasn't in a galaxy.
In 1926.
No, the pictures were taken in 1926. He was a graduate student
Okay.
who over the Easter break had nothing better to do, so he heard about this discovery and he thought he'd see if he could find an optical component for it.
Ah.
And he did.
Mhm.
And so he was the guy that got the that actually prove that these things did exist, and you actually had a picture.
Huh.
Yeah, it was very serendipitous in the fact that that discovery plate, the drive on the telescope wasn't tracking.
Right.
So the stars were trails, and there was this spot.
Oh, wow.
And he figured out the hyperfocal distance. It couldn't have been fireflies can't fly that high. He went through this elaborate analysis.
What was his connection to this DAS? He said he
Well, he was a
forever.
student member here back in the 70s.
I'd never heard that story. You know what? I actually spent about a year and a half in grad school working in the room right next to the Harvard plate stacks.
Yeah.
So I need to go back there and look.
Yeah, this
something about
picture
that.
was
That's
actually in National Geographic.
Yeah.
Yeah. Oh, and just as another aside, Brad was also a co-author on Salt Perlmutter's prize-winning paper.
Oh, yes. About a totally different type of supernova that I did not even talk about tonight.
Yeah.
Do we have time for a couple more, or do we need to get going? Because I see more.
We have time for as long as you have time and people are interested in asking questions.
Okay,
So,
go ahead.
This is not a heavy question at all, but it's a supernova occurred in 1044. How do you something know that happened? You didn't write 1044 on a piece of rock.
No, China was keeping extraordinarily accurate calendars. And that was how we were able to determine that. And it was, I think, China, Japan, and Iraq all had very accurately dated records of the supernova that dovetailed with 1054. I think we were even able to get it, it was the 4th of July that it happened. I think we were even able to get it down to that out of historical records. And then from studying the remnants of the nebula, we could corroborate that. Because you see how fast the material is expanding out and hit rewind to imagine how long it would have taken, how long since the star detonated, we're looking at it. And from there we got back to the exact same date. But the historical records actually were quite accurate.
yeah, but I think he's asking about how do you date the picture of the star on the rock in Chaco Canyon?
Right, yeah, it could have been 1640.
Right.
Yeah.
Yeah, but
They
there
have
was no
those-
supernova in 1640.
Well,
There was a supernova in 1604. Part of it was possibly just looking at the relative positions and matching them, but I think it also had to do with the history of the civilization that was there at the time.
Yeah.
And the folks that were there at the time and what event it would have coincided with.
And it was also the moon as well.
Yeah, the moon helped a lot. I don't know how accurately they're able to date something like a petroglyph. I don't know what kind of analysis you can do on that, but I don't think they can do any kind of chemical data or anything like that. I think it was the age of the society relative to when it happened.
Yeah, I think probably the way they dated that was in 1604, 15, whatever it was, the Chaco Canyon civilization was no longer there.
It's gone, right?
It's
Yeah.
been run out by drought and other things.
Yeah, it's interesting how history impacts this, because there's a reason. The 1054 is obviously in the Northern Hemisphere, and I was listing off who has records of it, and Europe does not, because other things were going on in Europe in around 1054. There wasn't a whole lot of astronomy happening. The supernovae in 1572 and 1604, though, were studied by Tycho Brahe and Kepler, and we have very detailed European records of those.
okay.
Still had no telescopes, so.
Not like what we have now, unfortunately. Yes.
On the subject of weirdness, did WR stars, why did they not make the list?
I ran out of time. and honestly, part of the fun of doing something like this is my research, sort of by accident, has wound up being studies of weird massive stars. And Wolf-Rayet stars are not something that I have worked on yet. I was able to actually highlight mostly research that I have done. I have colleagues that are experts on Wolf-Rayet stars, and they're stars that I really want to study, but I haven't done a lot of work on them yet, so they unfortunately got.
One of the missions of the James Webb Telescope is to look back as far back in time as we can see, to try to see the very earliest stars or galaxies just after. How will that affect the work that you're doing?
I think the most interesting effect it'll have is it's actually affecting the work that I'm doing now, believe it or not, trying to get ready for James Webb. So an interesting thing about gamma ray bursts is that we can see them out to astonishing distances. The current official record holder for the most distant thing that we have seen is a gamma ray burst. It is 13.2 billion light years away. if I'm getting this right. It's from a star that exploded in the first 500 million years of the universe, which is incredible. We've seen the explosion and the death of one of the earliest stars that we think was made. We can get a certain amount of information from a gamma ray burst when it happens, but most of what we know about them has actually come from studying the galaxies where they happened. This is actually what my whole PhD thesis was. It was finding galaxies that gamma ray bursts had exploded in and looking for commonalities between them to see if there was some recipe in the environment that helped to make one of these. That distance means that we detected the gamma ray burst, but we have no hope with what we have now of detecting the galaxy. With James Webb, we should be able to. We should be able to at least get an image of it. For one of these slightly more nearby ones, we should be able to actually get a spectrum. So then we're measuring the chemistry and the actual, light properties of the galaxy that hosted that burst, which is the best that we can do. That's the galaxy where that star was born. And the reason that that's informing what I do now is because James Webb detects light in the infrared. And that galaxy is so far away that what we are getting as infrared light from that galaxy was actually ultraviolet light when it was emitted. This is the principle of redshift, that as something moves away from us, the light gets shifted redder and redder and redder. It's so dramatic at that distance that the ultraviolet light is what we'll be getting in the infrared with James Webb. And we have really limited capabilities in the ultraviolet right now. Most ultraviolet light we can't observe on Earth. We have to go to orbit. Hubble is perfect for observing ultraviolet light. That Hubble program that I described of observing ultraviolet emission from galaxies was basically preparation for James Webb. We want to try and get a really good picture of what galaxies look like in the ultraviolet while we can, so that when James Webb turns on, we'll have some idea of what we're looking at. So that's how it's informing what I'm doing right now.
I've read that the earliest stars, the very first stars in the universe, which were of course made of almost pure hydrogen and helium, must have been extremely massive in order to form at all.
Yes.
Thousands of solar masses,
Yep.
perhaps.
This is where these 300 to 1,000 solar mass stars come in.
Right. That would make a pretty big boom, yes.
Potentially. It depends on, it would certainly make a dramatic supernova, but I have no idea if it would be bright. We don't think it would be bright enough for us to see from Earth.
Even with James Webb.
Even with James Webb, we don't think so. Yes.
Yeah, it was just kind of a burning curiosity. I seem to remember a computer simulation that somebody had done, that here's the sun, and here comes a white dwarf. And it reminded me of Edgerton's photograph of the rifle bullet going through an apple. Little hole on the way in, and it just blows the star all to smithereens.
Has anybody seen this Edgerton photo? Any of the stars? Okay, yeah.
Yeah, so the question is, how can one of these red supergiants swallow a neutron star and not have it come apart?
Red
Doesn't
supergiants.
hit the center.
Well, it doesn't have to hit the center. It can spiral into the center. But neutron stars are extremely tiny, and red supergiants, for as large as they are actually really puffy and diffuse. So you could easily fling a neutron star into the center of one and have it interact with relatively little matter. It would not interact at all, but it would be much less like shooting a bullet through an orange and more like rolling a marble through a pub or something like that. You'll see a disruption, but the difference in density and the difference in the two objects.
So the low density of the red supergiant is what keeps it from coming apart.
Sort of atmospheric breaking, except the neutron star can't burn it.
Yeah, what we've actually talked about, I was talking with somebody about this a week ago, is looking for the signature of that formation, seeing if there's any sort of ringing that happens if the star gets hit with the neutron star and then kind of falls back together. And the problem there is that every red supergiant does that, and every red supergiant is very strange. And we'd have to understand red supergiants extremely well before we could decide that one of those was due to a TZO instead of just a normal star being weird. So a lot of times we just wind up giving ourselves more homework when we do something like this. Yes?
The question was, you went over the formation of black holes, what about the formation of supernovas?
Okay, yes. Supermassive black holes are the same concept, because you have this idea of an infinitely small, infinitely dense thing. The formation mechanism is totally different, despite them having the same name. Supermassive black holes are formed at the centers. We have a supermassive black hole at the center of our galaxy, and a lot of galaxies that we know about have their centers. I do not know exactly what the formation mechanism is for them, other than a black hole like the kind that I talked about is about a solar mass. It's the mass of a few suns. One of those is the mass of 10 million suns. So I'm not sure if it's a consequence of the galaxy's formation and piling an extreme amount of mass into the heart of the galaxy, or if it's something that forms over a slower amount of time. I'm no experts on this, so I'm sure can answer your question better than me. But all I know is that it's quite different than how you make a stellar mass one.
So, with regard to what they were talking about, the first thing that struck me, like when you were talking, was you talk about like, gee, it could be a supernova, and you shoot basically a rifle bullet into this other partner star, and you have that, blah blah blah. But what struck me first, and now what they're saying, it's sort of like this related question, is that, well, it may not actually hit. Have you done any research about, well, what if it goes on near pass and becomes something that's dwarfed, they attract each other, da-da-da-da, and they sort of evolve, and at some point one captures the other, they capture each other with lots of them. So it's not necessarily a smush, but okay, near miss, and then it goes. It's not going to escape, right? And then with regard to what they were saying, same thing. We're sort of in this habit of assuming, okay, well, one went together, now they're combined, but is it possible, or have you looked into the possibilities of it going through, and then again, that sort of orbital thing until they finally, like multiple entries through the same star?
The end result of that would probably be the same. If you have two stars in a binary, the binary is eventually going to decay, and the red supergiant will consume the neutron star. It gets into a semantic difference between swallowing the companion versus the companion getting shot in.
Right.
Because at some point, it turns from the shot-in scenario to the engulfing scenario.
Sure.
There is an alternative version of this that does not make a Thorne-Zytkow object, and you don't even need a red supergiant and a neutron star to do it. You would need a red supergiant and any smaller, more compact companion, where that companion goes spiraling in and is in a very close binary orbit, and rather than just passing harmlessly through, it actually starts ripping off the outer layers of that star and stripping away, for example, that hydrogen layer of the red supergiant. We think this is a way to potentially make Wolf-Rayet stars. This is actually a potential idea for how we could even make some types of supernovae. That you would rip off the outer layer, then slam that companion star, again, not a neutron star, something bigger and less dense, but still denser than the red supergiant, slamming that companion star into the core and creating a supernova that way. So it's an alternate idea, but it gets into this idea of, yeah, what if it's delta glancing below and kind of pops in and out a few times.
When does it even have to go into the core? I mean, what you're saying, and essentially, most of the stars that we're talking about had some sort of equilibrium, and the story of stellar evolution is, okay, well, that equilibrium is temporary, and then there's sort of a recalculation and a rebalancing, and except for when there's too much mass, whatever, when there isn't a rebalancing, and then poof, right? So, if it were to go through and just strip off enough of the outer atmosphere, you'd be out of balance. You could have a nova or a supernova that way.
You wouldn't necessarily have a supernova. You might lose a lot of those layers, but the source of the equilibrium is that core. So we assume that anything that is a supernova level event, anything that destroys the whole star, has to at some point involve the core. There's something you had said that caught my attention when you were describing this. Yeah, we assume that to make a supernova, you would have to involve an interaction between the two cores. What we actually do have, though, we have things called common envelope stars. I think there's an example of a red supergiant or a red giant with a white dwarf basically just like stuck on the side.
Right.
They're binaries, but they're evolving inside one atmosphere, basically. They're evolving inside a common envelope, so it looks like a red supergiant with something stuck on it.
Right.
And stars can survive like that for a while. They're just in a very tight binary orbit, and they're exchanging mass and losing mass at such a rate that it looks like one star with a very strange spectrum in it.
Is that type of cataclysmic variable?
I know some of them are, and I can't remember what some of those are cataclysmic variables. A lot of times these start to get into really obscure types of stars that are named after the first star that they found, so it's an R-core Bohr star or like a BX Mu, whatever the name of the first star was, but there are multiple examples of a red supergiant or a red giant with a white dwarf stuck on, and there are specific lines and specific properties that are indicative of that. I just can't remember the name of the class. Yeah, no, I'll remember it on my drive.
That's also a matter of degree too. I mean, there's other stars that are like beta lyric or get to be ridiculous. So it's like
exactly.
At what point you say, well, they're separate, they're not, it is or that, it's like,
And what point you start naming them differently based on how they look. It's a continuum rather than distinct stages. Yeah.
Or does it force a co-rotation? Do they become kind of lost?
Sometimes. That's really hard for us to tell. We assume based on the physics that they must belong, but most of what we see in that one is the chemistry of the stars. We should probably do that.
Any further questions?